Hello everyone, welcome back. In this video, we're going to work together to derive a very important trigonometric identity or formula, what we call the sum and difference formulas. These sum and difference formulas that we're going to derive together are going to have lots of important and useful applications in our class and other classes. They're going to help us solve new equations, evaluate our trig functions at new angle values, and they're also going to be very helpful for deriving even more useful trig identities and formulas. So we're going to be using the unit circle and some geometry to help us derive these formulas. And the first sum and difference formula we're going to work at deriving is going to be our cosine difference formula. And so what this formula is going to help us do is we're going to be able to take cosine of a difference of two angles and express that in terms of a combination of sine and cosine of those individual angles. So like I mentioned earlier, we're going to derive this formula using the unit circle and some geometry. And to help us get started drawing the necessary picture, let's go ahead and choose two angles, A and B. So it doesn't really matter which angles we choose when we draw this picture, but for the sake of drawing the picture, let's go ahead and say A is our larger angle and it lands in the second quadrant, and B is going to be our smaller of the two angles, and let's just say that that lands in the first quadrant. The way this argument is going to be set up and work, it doesn't actually matter where we put A and B. We could put A down in quadrant 4 and leave B in quadrant 1. Any combination is really going to get us the same result. So we don't know what these angles A and B actually are, but we can still express their x and y coordinates using that unit circle definition of our sine and cosine functions. Remember, the cosine function of an angle or arc length gives us the x coordinate corresponding to the point on the unit circle associated with that angle or arc length, and sine of our angle gives us the y coordinate. So if we're at this angle or arc length corresponding to angle A, then we know on the unit circle the x and y coordinates of that point are going to be cosine of A and sine of A respectively. Similarly, over here at angle or arc length B, we know the x coordinate will be given by cosine of our angle, and the y coordinate will be given by sine of our angle. And so far we've just really used our unit circle stuff. I also said there's going to be some geometry that comes into play, and this is where it starts. What we're now going to do is create a little triangle within our unit circle by connecting these points at A and B together, and then connecting the point at A to the origin as well as the point at B to the origin. And so now we're going to use another useful fact from geometry, and that's that if you take an object like this triangle here and you just rotate it, that's not going to change the lengths of any of the sides of the triangle. So our next step is to rotate our triangle clockwise so that this side length going from the origin to point B lands on our positive x-axis, and we can actually measure how much rotation is needed there. That's corresponding to our angle or arc length of B. That point that was at B is going to get rotated down to the starting point on our unit circle. So now we really know 2 points on our green triangle so far, the origin 0, 0, as well as the starting point on our unit circle 1, 0. We need that third point though to finish this off. Well, we went from this point to this point using our angle B to rotate it the appropriate amount, and we're going to rotate the rest of our triangle by that angle B amount as well. Well, when we're talking about angles, that's like moving in the negative direction, so we can also think of that or visualize it as subtracting an angle B from these other angles within our triangle. Right, so if we do B minus B, we end up at the angle or arc length of 0 on our unit circle. That's another way of thinking about getting to that starting point 1, 0. And so we can also rotate this point that was at point A, an angle B clockwise. That's like subtracting an angle of B or an arc length of B from that point A. And so that'll land us at the angle A minus B. And so that's going to give us a third useful point on our unit circle, the one we're actually going to use in helping us derive our difference formula for our cosine function. Just like we saw it before, we know that the x coordinate of a point on the unit circle corresponds to cosine of the angle associated with that point. So the x coordinate of the point at AB will be given by cosine of A minus B, and the y coordinate will be given by sine of our angle, so that's sine of A minus B. And so now we can finish drawing in our green triangle here by connecting the origin to the point at A minus B and the point at A minus B to our starting point at 1, 0. So if we call our starting point S, then what we can see in our little geometric picture using these triangles and rotations so far is that this length of our triangle, the side length from A to B, that's one way to denote it using some of that geometry notation. That's not too important here, but the length of a side from A to B is going to be the same as the length from A minus B in our green triangle to our starting point S. So these two side lengths are going to be equivalent in length. Of course, the other side lengths in the triangles are also equivalent in length, and those are going to be side lengths of 1, which we can find and see just from the radius of our unit circle. Remember, the radius of the unit circle is always 1. And so this is our really important and crucial observation. What this tells us is the distance from this point at A to this point at B is the same as the distance from the point at A minus B to our starting point at S or 1, 0. And so now we're going to be able to use our distance formula from earlier classes to kind of express these equivalent or equal distances together using their x and y coordinates. But that's going to equate the distances together using sine of A, cosine of A, cosine of A minus B, and sine of A minus B. And that's where our difference formula for cosine is eventually going to come from. So we have to remember our distance formula in order to build this up and put it all together. And so remember the distance between 2 points. And so remember the distance between 2 points is always given by the square root of the difference between the x coordinates squared added to the difference between the y coordinates squared. Right, this is really just a consequence or corollary of the Pythagorean theorem. We can always draw a little right triangle between 2 points, and the distance between them corresponds to the hypotenuse in that right triangle. And that's where this distance formula is really coming from. So let's go ahead and start by describing the distance from A minus B to S. So we're going to have to look at the difference between these x coordinates squared and add to that the difference between these y coordinates squared. First point, that's first green point, has an x coordinate of cosine of A minus B. So that is like our x2 value. Our x1 value is going to be the other point's x coordinate, and that is positive 1. So our y value for our first point is sine of A minus B. And we have to subtract away from that the y value of our second point here. That y value is 0. And so that is our distance from A minus B to S. And now we know just through the rotational preservation of our distance here that this distance from A minus B to S is going to be equal to or exactly the same as the distance from A to B. So now we just find or express the same distance using the x and y coordinates for our points at A and B. So the difference between those x coordinates squared can look like cosine of A minus cosine of B. And whether you do the difference in the opposite order, doesn't matter. We'll get the same thing in the end once the dust clears. So that is the difference between our x coordinates squared, that piece of our distance formula. We have to add to that the square of the difference between our y coordinates for these 2 points. That's going to be the difference between these sine values. So that'll be sine of A minus sine of B. That quantity has to get squared, and we can't forget our square root over that quantity. So this green quantity set equal to this pink quantity is just our way of algebraically saying the distance from A to B is equal to or the same as the distance from A minus B to S. To finish it off, we just have to do some algebra and solve this equation for the quantity cosine of A minus B. So let's go ahead and start doing that. And one thing that will help us do that is to get rid of the square roots involved in both sides of our equation. And we'll do that by squaring both sides of the equation. So we're just eliminating the square roots. So there we have it. We just have the square of the left-hand side set equal to the square of the right-hand side. So our next step in deriving our cosine difference formula is expanding all these quantities and combining like terms. All right, this is looking a little bit messy, but we can start cleaning it up if we use some of our earlier identities that we talked about. In particular, that Pythagorean identity. Remember, our Pythagorean identity says that sine squared plus cosine squared is always going to be equal to 1 as long as the angles or inputs of sine squared and cosine squared are matching. That's exactly what we have here and in a few places in our equation. Right, on the left-hand side, we have cosine squared of A minus B plus sine squared of A minus B. We can combine those together, use our identity, and replace that or substitute it with a constant term of 1. So we can add this one along with our other one on our left-hand side to get a 2. So our left-hand side is going to look like 1 plus 1 is 2 minus 2 times cosine of A minus B. We have some similarities on the right-hand side. On the right-hand side, we have cosine squared of A plus sine squared of A. That turns into 1. We also have a cosine squared of B plus a sine squared of B. That turns into another 1, giving us a grand total of 2. So on the right-hand side, we have a constant term of 2. We also have a negative 2 cosine of A, cosine of B, and a negative 2 sine of A times sine of B. All right, it's starting to clean up pretty nicely, and we can actually finish it off with just a few more steps. The first of which is to notice there's a constant term of positive 2 on each side of this equation, so we can subtract 2 from each side and cancel those out. And then once we've canceled out that constant term of 2, we can notice, well, everything left in our equation has a constant coefficient of negative 2, so we can divide both sides of our equation by negative 2 and cancel that factor out. And once we've done that, we've arrived at or derived our cosine difference formula. It says cosine of A minus B, that's our left-hand side, is equal to cosine of A times cosine of B plus, because remember these double negatives canceled out when we divided, plus sine of A times sine of B. And that is our difference formula for our cosine function. What it allows us to do is take cosine of a difference between two angles, like maybe two known angles. That difference might give us a new unknown angle that we didn't know about previously. And what it really allows us to do is express cosine of this complicated A minus B angle in terms of sine and cosine of hopefully these simpler angles, A and just B. Hey everyone, now that we've derived our cosine difference formula that we see on our board here, we're going to see how we can use this formula to derive many other useful trigonometric formulas or identities. So the next one we're actually going to look at is how to find our cosine sum formula instead of our cosine difference formula. So to go from our cosine difference formula to our cosine sum formula, we just have to make a substitution. The idea is this formula for cosine of A minus B is going to work no matter what our angles A and B are. So what that means is we can swap out B with anything. We could swap B out even with negative B. So what we're essentially doing is we're setting B equal to negative B in this equation. So we're just going to go through and replace every B that we see with a negative B. Our initial motivation for doing this is it makes the left-hand side of our equation become cosine of A plus B, so that's working towards our cosine sum formula from our cosine difference formula, and that gives us the right-hand side expressed slightly differently in terms of sine of A, cosine of A, and sine and cosine of negative B. We're going to be able to do a little bit more work here and simplify the right-hand side of our equation, but we're going to have to remember another one of our properties of our sine and cosine function, and that is their symmetry. Remember, our cosine function was an example of an even function and had that symmetry about the y-axis. It's cut perfectly in half by the y-axis. One of the algebraic properties of a even function is that if you evaluate your even function at a negative input, it's exactly the same as evaluating your even function at the positive input. So what that is basically saying is that instead of writing that as cosine of negative b, that's exactly the same as cosine of positive b, right? Cosine of negative b and cosine of positive b are the exact same thing. And we're using that fact here to rewrite the right-hand side. We're going to use a similar corresponding property for our sine function. However, if we remember the symmetry of our sine function, it wasn't even, it was one of those odd functions. The odd functions have that rotational symmetry about the origin, where a horizontal reflection is the same as a vertical reflection. And so sine of negative b we can think of as a horizontal reflection, or we could also think of that as a vertical reflection, which is negative sine of b. Another way of saying that is for these odd functions, if we have a negative factor in our input, we can bring that factor out and multiply it by the outside. So that negative 1 can be moved to the outside. It only works for the negative, not like any factor. But basically, we can rewrite this as negative sine of a times sine of positive b. So now we have our cosine sum formula. Cosine of a plus b is equal to cosine of a times cosine of b minus sine of a times sine of b. All right, from our cosine difference formula, we were able to make a substitution and derive our cosine sum formula. And when we compare the right-hand sides of those formulas, we see that they are very similar. And this similarity allows us to write them more compactly using a single equation or formula. And that's what I have in green here. This is what you'll often see in textbooks or on note pages. So our cosine sum and difference formula says cosine of a plus or minus b is equal to, or can be expressed in terms of, cosine of a times cosine of b minus plus sine of a times sine of b. The idea is the operation on each side of our equation corresponds. So if we have a plus on the left-hand side, it'll be a minus on the right-hand side. And if we have a minus on the left-hand side, that'll correspond to that lower operation, the plus or addition on the right-hand side. I want to very quickly derive our sine sum and difference formulas, or at least talk about how to derive them. So it's going to start with our cosine sum and difference formula, and also an important relationship that we observed earlier between our sine and cosine function, and that they are just shifted versions of each other horizontally. Right here I have a little sketch of our sine graph and a sketch of our cosine graph. And so what we want to do is kind of think about how can we express our sine function as a transformation of our cosine function. And what we can see here is our cosine function normally starts at a maximum, while our sine function starts at an equilibrium or midpoint and is increasing through that equilibrium or midpoint. So we can kind of see that going through an equilibrium or midpoint and increasing through it corresponds to negative pi over 2 on the graph of our cosine function. So if we want to transform this cosine graph and turn it into our sine graph over here, we have to take our cosine graph and shift it to the right pi over 2 units. Remember, if we want to shift a function to the right a certain amount of units, we don't add that number of units to the input of the function. Instead, we subtract that number of units from the input of the function. So if we want to shift our cosine graph to the right pi over 2 units, that's going to end up looking like, in function notation, cosine of x minus pi over 2. And so we're going to start by deriving our sum formula for our sine function. So we're going to try to figure out a formula that helps us evaluate sine of the quantity a plus b. And when we finish with this formula, kind of similar to what we saw for our cosine formulas, we want to express this in terms of just sine and cosine of those individual angles a and b. And so, well, how are we going to do this? Well, we're going to use this relationship along with our sum formula for our cosine function. So if we want to think of creating sine of a plus b, we can actually get started doing that down here. What do we have to do? We just have to replace x with the quantity we would rather have in the input, which is a plus b. Well, in this relationship here, if we swap out x on one side, we got to swap out x on the other side. And we see that we can now express sine of the quantity a plus b, that thing we're looking for, in terms of cosine of the quantity a plus b minus pi over 2. And now we're essentially going to do that same technique or trick that we used for deriving the sum formula for our cosine function. We're going to think of a as our first angle, and instead of our second angle being just b in our formula up here, we can swap that out with anything as long as we do it carefully. We're going to swap that out with b minus pi over 2. Now we can really start doing some important simplification. Not much we can do for that first factor in our first term. That's going to remain a cosine of a. But we can rewrite that second factor. What is cosine of b minus pi over 2? Well, using our shifted version relationship down here, we can see that if we just replace x with b, we see that we get cosine of b minus pi over 2 is the same as sine of b. So that first term turns into cosine of a times sine of b, and now we have to subtract away from that sine of a times sine of the quantity b minus pi over 2. So that first shifted relationship we saw helped us a lot with that second factor in our first term. We need a similar relationship for that second factor in our second term. So if we look at the graph of our sine function down here, this would be like sine of x or sine of b. What happens to our sine function if we subtract pi over 2 from its input? Well, that is going to shift it to the right pi over 2 units. In green, I have the shifted version of our blue graph, our sine function, to the right pi over 2 units. So that gives us sine of the quantity x minus pi over 2. And well, if we look at that starting point, or the point going through the origin, it's at a minimum. So that's going to correspond to a cosine function, but a negative or vertically reflected cosine function. So our first factor is still sine of a, but the second factor is going to turn into negative cosine of b, and the negative is going to combine with the other negative out front originally to cancel out and give us a positive. So what we see here is sine of A plus B is equal to cosine of A times sine of B plus sine of A times cosine of B. And that is our sum formula for our sine function. And so that is our sum formula for our sine function. And we can derive our difference formula for our sine function doing the same step or process that we used for our cosine function. Just swap out b with negative b and use some symmetries to simplify the other side. When we take the time to do that, what we find is sine of a plus or minus b is equal to cosine of a times sine of b plus or minus sine of a times cosine of b. So for this sum and difference formula, the pluses correspond to each other, as do the minuses. That's one easy mistake to make and to be aware of, depending on which formula you are needing to use.